Okay, so this is a continuation of a previous problem that we worked with, where we set up all the material balance and energy balance equations that we would need to solve and find parameters for in order to design a reactor for this system of three different reactions, all of which are exothermic. Okay, let's take a look at actually what happens when we plug these in. So I'll show a few more of these equations. There's our energy balance equations. Let's see what happens when we plug these into a solver program, which we're actually going to need in this case because there's no way to analytically solve this expression. And so we'll want a computer to hopefully solve it for us. Okay, so I'm going to switch over to the Polymath application. Okay, so energy balance expressions are shown here. Some of the symbology may have changed slightly, and so we see we have energy balances for the temperature and for the temperature inside the reactor and of the cooling fluid. We have our material balances for A, B, C, and D, and we'll see the material balance for E below. We have our rate expressions defined in terms of concentrations, our concentrations defined in terms of molar flow rates and other parameters, a series of constants that are defined, such as the initial temperature here. We have the heats of reaction defined. We've defined some rate constants as a function of temperature, which is important since this reaction is exothermic and we might expect the temperature to change. We've got overall heat transfer coefficients times interfacial areas here. And then I'll show maybe the other important thing here is the balance on E. E is produced at the same rate as D. I've got a selectivity defined here. And then I have specified the initial conditions that we start at the beginning of the reactor, not having seen any catalyst, initial temperature of 850 K, and so forth. Okay, and what we want to explore is kind of how perturbing a few of these variables really affects this exothermic reaction system, and we can see that trying to come up with an optimum is actually can be pretty difficult. And so let's just run this initial set of parameters. And I'm just going to point out that for this initial set, what I assumed was that we didn't use any cooling fluid. I've set a mass flow rate times heat capacity of water value as being very low, so that essentially there's very little cooling water flowing through the system. So just to see what an adiabatic reactor really would function like. Okay, and here comes the solution. This doesn't always plot it on the best scale, so we'll do some rescaling here. We can see what happened. This is the temperature. The green is the temperature of the cooling fluid. The blue is the temperature inside the reactor. Since we weren't flowing much cooling fluid, what's there heated up to essentially the temperature of the reactor immediately and tracks it throughout. We have a significant exotherm here, so the temperature sort of starts increasing fairly slowly, and then it begins to pick up and really take off and go to a fairly high temperature of over 1,000 Kelvin. And in some cases, this could be a potential safety hazard, and in fact, that's one of the reasons why cooling is often used is to help with safety. But we'll focus on a different factor, which is the fact that this high temperature actually doesn't allow us to produce much of what we want. I have to reformat this a little bit, but it's the maximum so that we can zoom in on the flow rates. And what we can see happens here is that we consume all of our reactants, or all of one of our reactants, the oxygen, is being completely consumed, so the reaction stops at that point. At a certain length down the reactor, we reach our optimum conversion to make our desired product, which is this small purple trace. But unfortunately, our main products are CO2 and water, as you can see from this predominant trace. And we sort of expect that at high temperature. At high temperature, the combustion reactions, which are more activated and more exothermic, will begin to take over. Allowing the temperature to get to this very high value is not good. Okay, so let's take a look at a case where we allow our cooling water to flow more rapidly and see how that improves things. So that again is the MCP term. So I'm going to make this more like 1,000. Now let's see what happens. Okay, here we see apparently superior behavior. Of course, in the last example, we had our cooling water going up to over 1,000 Kelvin, which is never a good idea. This even may be too large of an increase, so we may want to improve things a little bit. We see that our temperature rises and then starts to come down, but it still rises quite a bit. So on this scale, it maybe doesn't look much, but it's close to 400 Kelvin. All right, let's zoom in on what happens to our molar flow rates. Tedious here. Okay, that we again consume all of our oxygen. That's almost never going to be a good thing. And we really still don't have apparently enough cooling water. We see some formation of ethylene oxide here, but really not sufficient conversion. We again are getting this behavior where we level off with CO2, so it's still not good enough performance. Okay, so one issue is that we may just be operating at too high a temperature to really prevent formation of CO2, and so maybe we should try to decrease our initial temperature. And so I'm going to take this down, let's say fairly significantly, I guess 650 even, and expression for T naught somewhere else. Okay, so 650. Let's see what happens here. Okay, now we're see something interesting, that by lowering the temperature to that extent, okay, we actually are having a decrease in our temperature. So the exotherm never really takes hold, and we have a significant decrease in the reactor temperature right from the outset. Okay, and so we can zoom in on this behavior, and we see that we get a little bit of reaction. Okay, so things are decreasing a little bit, but really very low conversion. We could continue to operate the reactor out to higher catalyst masses, so build a bigger reactor, and we would see a larger conversion. I'm going to zoom in on something else here, weigh in, I guess. Okay, and what we can see here is it's still not ideal, and we're still producing too much CO2. This evidently isn't a very good catalyst. All right, but now that we've gone to this very cool temperature, all right, the reaction is slower, but we're producing at least more of the desired product C than we are of D. All right, so we have an advantage during this lower temperature reaction, that we're not wasting our reactants to produce this undesired product CO2, but the reaction is just too slow. Okay, so we may want to increase the temperature a little bit in order to try to get a better behavior, or we could also try to increase or decrease the amount of cooling fluid that we lose in order to try to use the exotherm itself to do the heating. Okay, so if we increase this temperature somewhat, let's increase it to 700, to do that in two places. And now we see we start to get to a situation where the temperature is almost level. That's typically a pretty good result, that it helps you to keep your reactor under control. And so it's good to find conditions in which the temperature is pretty close to level. This still may be very far from optimal conditions. We're going to see that we get some more conversion here, but it's still probably not enough. Okay, so we're getting quantitative conversions, especially of oxygen, but still not desirable, or not fully desirable. If we look at we zoom in again, we see we're producing significantly more product on the same scale. Unfortunately, now that we're operating at this higher temperature, we're producing more CO2, which is the more activated process, than the desired product, although we're still producing a respectable quantity of desirable product rather than the tiny amount that we were producing. Okay, and so hopefully you can begin to see some of the trade-offs here, that as we increase the starting temperature, that we can get much faster reaction rates, but we have a greater danger of those reaction rates leading to much higher temperatures toward the exit of the reactor as the reaction gets out of control, and also lower selectivities to the desired product. But if we start at low temperature, we can get improved selectivities, but the rate is very slow, and we need to use a large reactor with lots of catalyst to get substantial conversions. And there are many other ways that we can eventually explore trade-offs. For the parameters that I picked here, it actually would probably be better to develop a better catalyst that is more active for production of the desired product in this case.